in the sake of time, maybe we shall move to the next research paper.
Deep neural networks for automatic structure discovery. So it's quite a tongue twister. And yeah, here's the agenda. I will start with an introduction, especially on structure discovery, and then continue with our approach, which is sample-based kernel structure learning. Then come to the experimental section and finalize with a conclusion and future work. Yeah, what's the topic about? It's about time series structure discovery. So when having a time series, what you often want to do is identify like the structure of a time series, and in the best case in an interpretable way. So here are two examples. So let's ask the question, how does the data look like? Then we see two time series where for the left picture, one answer could be it's a noisy periodic signal with slight positive linear trend and large periodicity. And on the right hand, you could say it's a noisy periodic signal with nearly constant mean and increasing amplitude. So amplitude is rising. And yeah, and what is this good for? So it's good for enhancing like structure, data exploration tasks, as well as comparisons based on properties of time series. Yeah, what has that to do with databases? So what are potential database applications? One potential case could be like labeling time series data or adding, enriching the time series data with further metadata, where we can say that specific time series data refers to a specific class and has specific properties or characteristics. And having this metadata stored, we could also do interpretable queries. We ask the database, give us all periodic signals with specific periodicity. And this at the same time also allows for similarity search. So when having this metadata and extracting new features from a new time series, then you could compare them and retrieve all similar items from the database. Yeah, and one way to perform interpretable structure discovery is by using Gaussian processes, where this work is based on. Here's a short reminder, so to say, what a Gaussian process is. It's a stochastic process and a distribution over functions. And you have generally it consists of two things, where the first thing is the mean function of all points, which is by default, or in nearly all cases, set to 0 mean because the data is normalized. And then the more interesting part is the covariance function, which characterizes the time series data. And the good thing is that when you take a finite set from some continuous space, the resulting distribution, if we assume it's Gaussian, is again a multivariate normal distribution. So every point on is distributed Gaussian, normally, sorry. And then here we see the normal distribution, which is then again having the mean function and the covariance matrix telling the correlations between individual points. Yeah, and what is the good thing with those correlations or these covariance functions? Kernels, which is just a synonym in this case, they reflect specific characteristics. So when we have, for instance, this squared exponential kernel, and we measure, we compute this distance or similarity measures rather between individual points. In the end, we see that the resulting signal is like a fitting, which is kind of a weakly function. And on the right, you can see some exemplary signals where we have a linear function, periodic kernel, periodic kernel, squared exponential kernel. And what we want to do is we want to fit those Gaussian processes and see, based on the goodness of a fit, whether it's rather a periodic signal or some linear signal. And also one further benefit is that kernels are closed under addition and multiplication. So we can create complex yet interpretable descriptions. So saying that, for instance, here we have a periodic signal with linear trend, or some signal which is linearly increasing, because here is multiplication, so the second term is linearly increasing. And this leads to the fact that the goal is to find the most appropriate kernel to say what the actual best fitting kernel for a time series is. There is one problem, because kernel search and kernel hyperparameter optimization is computationally expensive. I mean, there are a lot of work done to find efficient kernels, using, for instance, like optimized grammars and stuff, or optimize the regression process itself. But we thought, since you can also like sample from this normal distribution, which gives you the ground truth, why not simply, instead of doing the inference, why not just learn the actual ground truth so that you can do prediction based on new data? So it's a completely different approach to the inference. And I mean, although like the Gillespie decomposition also has cubic runtime, you could use like the decomposition to sample many instances, and therefore it gets efficient again. So and you also only do it once, so you can sample a ground truth and you can use a model like neural networks. Here we use neural networks because of the general effectiveness of neural networks, to build a model that can predict future time series classes, like of behaviors. And yeah, we would then only train it once to predictions in nearly none time. So what is the approach called SKSL? First, we do the sampling based on properties from specific or predefined ranges to get a lot of data. So here we can infinitely so to say sample data which corresponds to the ground truth, and saying, okay, this is linear data, this is periodic data, and so on and so forth. And then, since we have different lengths, and we chose a model which with a fixed length, we used fast Fourier transforms as a pre-processing step to get to a configured length, pre-configured length. And so this is like a first version, so to say, since this is rather considered a concept paper. And then what we would do is kernel structure and hyperparameter learning at the same time. So what we want to learn is the class of the kernel and also the hyperparameter. Here's a maybe more understandable overview of what we will do. So we can sample arbitrary signals. Then we would do the pre-processing to get to a predefined length. And then in the end, we could train on this data and doing the classification and regression at the same time. And in the end, having this model, when getting new data, we would also pre-process to get to a fixed length by down or up sampling via fast Fourier transforms. And as a result, we would get some output saying, for instance, that it is a linear plus a periodic signal, and having a specific noise and let's say the amplitude of the periodic signal. This would then be the approximation. So there are some assumptions and restrictions, of course. What we didn't include is change point detection. So there are time series that are like consisting of different individual behaviors. And what could be done in the future work as a pre-processing step is also change point detection to split this up. Then here we used as a first version, as I said, or a very naive solution, we used fast Fourier transforms to get to a specific input size or input length. And then here we are talking about, since we have a fixed number of classes, we are talking about a predefined set of kernels and kernel combinations. This looks like a drawback. In some situations, it might also be, but on the other hand, if you think about very, very complex, long kernel combinations, then you also, you raise the problem of the lack of interpretability. So when having linear times periodic plus linear times periodic again, and so on and so forth, it can become hard to interpret in the end. We thought of different different architectures, although the focus is not on architectural search, but in the end we came up with LSTM followed by some regularized dense layer architecture, because in our tests, I mean, we didn't test too much, but in our test this proved to be showed the best results. And as you can see, in the output layer, we have a dense layer for the number of classes and a dense layer for the number of for the hyperparameters. So the first output corresponds to the prediction of the class, and the second one corresponds to the regression of the hyperparameter. So it's classification and regression at the same time. In our setup, we chose, similar to other papers, we chose those kernels, which are linear kernel, periodic, squared exponential, and white noise kernel. Those are, let's say, the most prominent ones in many scenarios. And also pairwise kernel combinations. So in the end, we have 10 kernels for the experiment. And for those kernel combinations, we also randomize the hyperparameters like amplitude, periodicity, and also the length of the time series, and so on and so forth, of course, in a predefined range. But we also normalize the data so that it fits in the end. And we sampled 1 million time series data, although you could continue sampling all the time. And we had a train validation split of 80-20. And as a baseline model, we used a very naive model, which is a Gaussian process regression based on a variational inference of 2000 iterations, and using the ADAM optimizer, which was also the optimizer for the neural network. And we used this setup to then classify 100 random time series with equidistant indexes in the range of -1,1 for individual length. Here are the upper of the experience. I mean, the experience, it's rather like a baseline experimental setup. So we have in table 1, the kernel class accuracy and the hyperparameter loss for our approach, so SKSL. Then in table 2, we see the comparison compared to the baseline model called GPR for Gaussian process regression. And then we have a comparison for the prediction time, where we excluded the training time of the network because you do it prior to that and you only do it once. So during prediction, you only have the inference of the neural network. And as you can see, for the default length, so it was set to the default length, 500, we reached an accuracy of 87%. But on the other hand, you can also see the impact of the naive version of free sampling. So we see that when you had time series, which was way smaller, it was only 42% already. And for longer time series, which were downsampled, we came to, let's say, 76%. So you can see the impact of free sampling. Therefore, in future work, we definitely have to improve that. And in comparison to Gaussian process regression, we have to say we outperformed them, although this is a naive approach, which also might be because Gaussian process regression was not regularized. So in many cases, it could be that increasing the flexibility due to kernel combinations, the regression would rather choose like the more flexible model, although it was just a base model with one kernel. And the big factor is, of course, the prediction time. So since with Gaussian process regression, we have to do inference all the time for every combination to find the most appropriate model. We ended up with runtimes of, let's say, 5 minutes, and for our approaches, it was only 2 seconds, and independent of the length, rather. And on the right, you can see like the behavior of training, where it saturates quite fast, so that in future we should consider more complex models to improve this behavior. yeah, what are the pros and cons? So what we introduced was or I introduced was a new alternative approach for kernel-based structure discovery. So it's an alternative to all the traditional approaches, and some first experiments, although it was like a very naive experiment. It were quite naive experiments. It showed an accuracy of 87%. And we only have to train it once. So once the model is trained, we can at least do an approximation of the kernel class, and we can efficiently and unconstrained sample the like new data, new ground truth data to learn from. The cons are it's a basic evaluation, so a naive baseline, and we have no consideration of change points so far, and the selected pre-processing is naive, and the neural network is also just a prototypical solution. So for future work, what we will do is we will come up with more detailed experiments, and we will also evaluate on real-world data sets. What we did now is just an evaluation on the ground truth, but getting new data, real-world data. We don't have a ground truth, but we can then, for instance, compare on the likelihood of the outputs. And of course, doing optimization of pre-processing and the neural network architectures, and also consider change point detection. And I didn't actually check the time, so I hope I'm still in. Those are the references from the presentation, and yeah, thanks for your attention. You're muted, in case you're.
Okay, now I can speak. Thanks, Alexander, for the great talk. Very interesting work. So while others are thinking about questions, I have one, a very quick one. So Alexander, actually we have a question from Nadia. So Nadia, you can go first.
Okay, thank you. Yeah, Alexander, very nice presentation. I was sorry if I missed that. You probably mentioned that, but I missed it. So what are the traditional approaches for figuring out structure in time series? Are they also machine learning based, or is it something totally different?
No, they are also machine learning based. So the thing is that while you have different individual kernels and kernel combinations, this naive approach I just presented, it's trying in a brute force manner. It's doing variational inference and then trying to find the best fit and maximizing the likelihood of each fit, and then the highest likelihood, so to say, would correspond to the model. There are also more advanced approaches that, for instance, they try to present a specific kernel as a neural network, and also there are optimizations of kernel search as such, so that you, instead of going through every combination, you would start with the baseline kernels, and then you take the best fitting baseline kernel, and you only go this path in the tree, so to say, and then you expand it further, but it's depth first search, so to say, and not going wide and using it in a brute force manner. So I hope this answered your question.
Yeah, I see. Thank you. Thank you.
Thanks, Nadia and Alexander. So Alexander, I think I will simply skip my question, take it offline for the sake of the time.